At last, we are live in Information Theory, Lecture 23. After a long technical introduction that had nothing to do with information theory, but instead had to do with the vicissitudes of AirPlay, Camtasia, the iPad, Apple's AirPlay TV, and in any event, I'm not going to talk anymore about that. Okay, so today's Information Theory, Lecture 23. Today we're pretty much going to concentrate on rate distortion. We are here. Where are we? We're here. Lecture 23. Okay, so we have our standard reading, which, and for the most part, I think people should be reading and enjoying this chapter, chapter 10 in our book. But I wanted to also just mention that there are a number of other readings that you should start doing, and some of which we're going to be drawing from. And now is no better a time to actually start becoming aware of these sources. The first are these classic papers by Blahead and Aramoto, which actually the algorithm, the Blahead-Aramoto algorithm, is named after these two individuals who wrote these classic papers to compute both the capacity of a channel and also to compute the rate distortion function using a procedure which ended up being shown later on to be equivalent to not only the EM algorithm that's used for maximum likelihood estimate in statistical models, but also shown to be identical to the alternating minimization procedure, which we're going to go over. And so if you want to get a sort of historical account of what happened, I mean, you could read the Blahead paper, the Aramoto paper. There's a paper by Dempster, Laird, and Rubino about the EM algorithm, which I haven't actually listed here, but then these were generalized by Scissor and Tusneri, which I'm almost certainly mispronouncing. And then there's a very recent, well, relatively recent tutorial, which contains everything. So this 2004 tutorial covers completely the 1983 paper. So you could just read that. So you start reading those guys. This material is not in the book, I should also mention. But these papers are readily available. I gave you links for these two bottom papers you can get by a Google search. Or a Bing search. Or a Alta Vista search, probably even. So homework 1, again, is due on Monday at 11:45 p.m. It's 4 problems. So don't be comforted by the fact that it's only 4 problems and think that therefore you can do those problems in 40 minutes, 10 minutes for each problem. Please do start on the problem set now if you haven't already. I mean, you've had a lot of time to do them, but don't wait. Maybe 1 problem per day would make the problems very, very comfortable. Office hours again. So if you have got questions of the problems, last-minute questions, you can come by on Monday, or you can again post email, whatever usual thing. Okay, so let's do a little bit of review. We did a little bit of analysis of the increased capacity of the feedback channel in the case of a Gaussian, when everything's Gaussian, the Gaussian noise case, and we found that the feedback channel in this particular feedback channel doesn't really offer much in the way of increased capacity. So this is sort of the sad theorem, not the soporific, the depressing theorem. So that's one thing we talked about last time. And then we went on and started talking about rate distortion theory. This is now a plot that we've seen many times in this class, both last quarter and this quarter, showing how there are limits to compression, which are here. And then there's limits to transmission, which is here. And in each of those cases, we were interested in the rates at which it was possible to achieve essentially perfect compression or transmission. Perfect meaning that if we're willing to spend our resources on increased block length, the probability of error decreases exponentially in that block length and essentially vanishes very quickly. And that's essentially what we mean by error-free communication, because we can make the probability as small as we want very quickly. But what we're talking about now is the context where we're willing to accept a certain amount of error as measured by a distortion function. And so we get a very different kind of picture. We're going to be seeing these kinds of pictures a lot, and I should be very clear that this picture should be extraordinarily... I should be clear that this picture should be clear. That this region here that I'm highlighting in green is the achievable region, meaning that a pair, which consists of a rate is, we're talking really about compression now, so it's a rate of compression and a given distortion, is possible to achieve, whereas anything below this thing down here is not possible to achieve. Okay, that's the unachievable region. And of course, it doesn't make sense to talk about negative distortions or negative rates. That's not really, we're only talking about the positive orthant here. So, any questions about this general setup? Because if this isn't clear, nothing will be clear to you. Raise your hand if this is clear. Please. Thank you. Oh, good. Everybody, this is clear for. Okay. So we talked, essentially what we're doing is we're doing vector quantization, where we're taking a region, which is the source alphabet, which consists of all this stuff here, and we're partitioning the region into regions within which we have one representative of that region, which is called the code book, or the code words. The code words of each region has a code word. The collection of code words for a set of regions is the code book. And essentially what we're doing is we're essentially saying, regardless of where in the input space we go, what we're going to do after compression is have some code word representation of the source, and as a result, we're going to end up with distortion. And there are these numbers of qualities or aspects that affect the quality of a code book, which consists of the following: the specific code words, these representatives, and number two, how many representatives we have, which is dependent on the rate. Because remember, when we have a block length, n is again going to be, lowercase n is representing our block length. And if we have r bits per source symbol, then n times r is the number of bits we can use for a block of length n. And so we have 2 to the nr possible code words. And so the rate is really the parameter we're interested in, and that determines the number of code words, or the size of the code book. And so you'd expect that as the rate gets bigger, we're going to do a better job. And at some point when the rate hits the entropy, in fact, we should be able to do perfectly. So the other thing that affects the quality of this process is how often each one of these things are used. And how often each one of these things are used really depends on the probability distribution. P of x, right, this guy. This is P of x here. And then the last thing that determines the quality is, in some sense, how we're measuring quality, which is entirely dependent on the distortion function. Because the distortion might say that even if a region is big, you might have a representative of that region for which the distortion function says that that's perfectly fine. The distortion might say, as long as you're in the region, I'm happy. And so the distortion can also give you a little bit of relaxation and slack or something. And then we have the expected distortion, which is how we're measuring everything. So I'm doing a little bit of review a little bit slower because it's been a week since we saw this. Some of us have seen this stuff. Of course, I'm sure that all of you have completely read and digested Chapter 10 at this point, right?
More or less.
More or less than more? So, okay. Rate distortion setup. This is a slide we'll see a couple of times this lecture. So we have a source, which draws source symbols from some alphabet according to a distribution P of x, IID. An encoder function F, which maps blocks of length n of these source symbols to an integer that ranges between 1 through m, or 1 through 2 to the rn, or nr. A decoder, then, which takes one of the integer indices. And so the compression really maps to a set of integer. The decoder then takes the integer and maps to one of the representatives. So the encoder maps to the index of the representative, not the actual value. So the idea is, like, for example, we might have blocks of text or something, and then the encoder might map to an integer. Now the integer itself is not something that we could be interpreting as text. That's the code which is the index. The code book is the mapping from the integer back to the code words, which when we, in some sense, decompress, we only get one of the code words back, not the original. A distortion function, which maps from pairs of input to alphabet size. So notice that these alphabets are not the same, x and x hat. Right? So x could be very big, x could be continuous, x could be all sorts of stuff. X hat is smaller. Maybe it's even in the case when x is continuous, x hat might be just a bunch of points. Let's say x hat might be countable. It still might be continuous. It's a countable set, typically. Finite countable set. And we have some you know, the distortion measures the cost. We're assuming the distortion is bounded within the confines of the constraints of the input representation x. That doesn't mean that like we can't use x minus x squared or something. X minus x hat squared. It just means that we're never going to see a distortion, an unbounded value of distortion. The Hamming distance is one example of a bounded distortion. We've seen lots of these. So to further set up things, we have a 2 to the nRn rate distortion code. Consists of an encoding function, a decoding function, and then a presumed distortion of this function. This is the distortion. Okay. So a given code also has a distortion. Right. So this is the distortion. There's a underlying distribution, probability distribution, a joint distribution. Well, over the blocks of like n. Okay. Okay. And then we can say a code is achievable, or a rate distortion pair is achievable. That means if there exists a sequence of such codes. Remember, it's a sequence in n, just like we've been doing. So a sequence from n such that when we eventually get big enough, we can make the expected distortion as close as we want to the given distortion. It's the same type of definition we saw before. So rather than saying the probability of error goes to 0, we're saying that the expected distortion goes to d. Okay? So it's the maximal, d is the maximum allowable distortion. We can make errors, but we're not too many. We're dependent on the distortion function. And this is the rate distortion function here. So again, let me make this clear, that this rate distortion function is the infimum over achievable pairs. So for given distortion, d, the R of d is in some sense the smallest rate such that there exists a sequence of codes with rate r and distortion d such that as you take n to infinity, it actually isn't over the distortion. That's what achievability means. So it's the rate distortion, in some sense, achievable function. And we made a distinction between this function here and what we were calling the information rate distortion function, which is the result of that optimization problem, which hopefully I have on the next slide. And in fact, I do have it on the next slide, which is right here. That's a different function. It's a result of an optimization problem, which says you take the minimum over all conditional distributions such that the constraint, which is, again, zooming in on this, the constraint is given by this. The expected value with respect to the joint distribution that uses p of x, which is fixed, and the conditional distribution, which is what we're optimizing over. We take the expected distortion with respect to that joint distribution. And over all such conditional distributions, we find the one that minimizes the mutual information. Then that's the result. That's the minimum mutual information. And so it's a rate. When last time we spent a bunch of time talking about why it makes sense, why this is a sensible definition, why this corresponds to a rate, why minimizing mutual information corresponds to a rate. We also talked about how in the zero error case this corresponds to minimizing an entropy that has zero error. So this is like this is an entropy. This is really an entropy, but it's an entropy with distortion. But in the case of a zero error case, x and x hat are the same. And it's the self mutual information, so it's the entropy. Okay. In which case there's no conditional distribution optimized over. We just use the identity. So this is an immediate, direct generalization of the entropy. Yep.
So you said that this is like a communication channel, right? So we are minimizing over I. So if we don't have that constraint, does that mean that the minimum would be like 0?
Yes, because...
So the solution is actually at the boundary which is defined by that thing?
Yeah, so, I mean, if we don't have the constraints, then I can choose a conditional distribution that's independent, right? And I can just say, okay, well, I've got all conditional distributions. I'm going to choose one that's independent, where p of x hat given x is equal to p of x hat for any p. And any one of those independent distributions will achieve a 0 of the mutual information, which basically means that compression, you're compressing at a rate of 0 bits. But if you're willing to accept that distortion of whatever that is, I mean, then I can compress down to 0 bits, right? I mean, in the simplest cases, when distortion corresponds to error exactly, and you can say, well, make as many errors as you want. How well can you compress? Well, I can say, well, I can compress down to 0 bits because I can just send you a random number and it will achieve that distortion or that error, right? And I've never stored anything about what you've originally wanted to compress. And the trick here is that that's often the case, that you can, to achieve a given distortion, D doesn't need to be infinite to communicate at a rate of 0. I mean, the distortion, and you're going to see a lot of these plots, so they get to this point. I don't have one of them here, but they get to this point that looks like this, where we get to this distortion point where the rate is 0. And so once we hit that distortion, which is finite, just sending random numbers achieves that distortion. And so we can compress at a rate of 0. I can compress, that's not violating Shannon's entropy limit because of the fact that there's errors. Shannon's entropy is in the case when there's no errors. Using our definition of what no errors means, again, with block length getting big and probability of error going exponentially to 0 and all that kind of stuff, which I always want to qualify in the context of this class, lest there be any lingering confusion. So, all right, so here we are, and we're still in review mode. This is the guy we're interested in. He's the one who I hope everyone at this point has an intuitive understanding of, at least some intuitive understanding, and how it's related to the lossless entropy compression. Last time we talked about how, I already said this, so I'm not going to go over this again, but we talked about, in just the last slide and last lecture, you can look at it on YouTube, we talked about how this corresponds to the entropy. Okay, so here's our first rate distortion function. This is kind of where we ended up. So this is a real rate distortion function. So basically it says, first of all, it's a particular source. So we're going to analyze 2 of these today. We're going to analyze the Bernoulli source and Gaussian source, and then colored Gaussian noise with a joint constraint. Those are the 3 cases we're going to analyze today. This is the first case. The first case is rate distortion for Bernoulli. So basically it's a random coin flip with probability of p of heads. We have a distortion function, which is the Hamming distortion. It's basically an indicator of error. It says either you get it or you don't. If you don't, you pay a distortion of 1. If you do, you get a distortion of 0. Hamming distortion. And the claim is, and what we're going to prove, is that this rate distortion function has the following form, which is that if the distortion, so it's a rate as a function of distortion, so if the distortion lies within this range, 0 and the min of p and 1 minus p, then the distortion goes down in this fashion. So h of p, which is fixed, so p is a fixed parameter of the source distribution. D is what we're doing, and what this is going to look like is really this magenta function here, which this is where I could really use a pointer just to point this part out. But that's how it goes down. So it's going to go down until at some point the distortion is going to hit this value p, right? At which point the rate goes 0 forever after, rate is 0. Meaning that at the point that the distortion is equal to P, I don't have to encode, I don't have to compress at all. I can just essentially do something random or do something arbitrarily, and I will achieve already a distortion of P or bigger. All I need to do is achieve a distortion of P. And remember, this is the infimum of achievability. But what we want to do is we want to prove the information rate distortion function. So here's a couple of other points. Maybe I've already said this. So when the distortion is 0, the minimum rate is the entropy. So let's zoom in on this point here. So in this plot, this point, when the distortion is 0, is exactly equal to the entropy here. Okay, let's zoom out again. So why is that? The distortion is 0, the rate is equal to the entropy.
That's the Shannon point.
That's the Shannon point. Because when the distortion is 0, there's no error. So we should be able to communicate, we should be able to compress down to a rate of the entropy. That makes sense. Right? As the distortion gets bigger, we can compress more. We can compress more below the entropy, but we suffer some distortion. And the cyan curve eventually gives the limits of achievability. And then when, like I already said, D is bigger than the probability of the Bernoulli, then random noise or some other arbitrary thing can achieve that level of distortion. And so we can communicate or compress at a rate of 0.
What if P is 1/3, then or if P is 2/3, isn't that the same Bernoulli distribution?
Yeah, remember we're taking the min of P, and so P is always going to be 1/3 without loss of generality.
That point P on your graph down there.
It's always going to be less than or equal to 1/2.
Okay.
Because of the fact that we are taking this.
Okay.
And in fact, when we prove this, we're just going to, without loss of generality, assume P is less than 1/2. Then we just don't have to deal with the min. Because it doesn't matter. We can flip the symbol names, and those are just the symbol names. So what matters really is the minimum of the probability. Okay. One thing again, so this is again on the intuition, and I've said this now a couple of times, but let's go through this very detailed in this slide. So in general, is it always the case that the rate distortion function is equal to the entropy at D is equal to 0, like we just saw? So remember, in this plot, we saw that at 0, we had this point. Is it always the case that when the distortion is equal to 0, that the R of D is equal to the entropy? So when we have 0 distortion, is the rate 0? Who says yes? Who says no? So who says, can it ever be greater than the entropy?
You're trying to trick us.
I'm not trying to trick you. I'm trying to teach you. This is not trickery. We don't go to the University of Washington to encounter tricks. This is, and our goal is to offer insightful questions to make you think about these problems and reach aha moments and epiphanies, and so that you can say, "Oh, I understand that." Once you thought about the question, and part of the reason for coming to class is sort of to be confronted with hopefully insightful questions that will help you guys to think. Helps me to think. These are questions I had. Actually, a lot of these questions that I'm asking you, to be honest, are questions I had when I was learning this material back in graduate school, and I wrote notes on my book. And so a lot of the things I'm doing are the questions that suddenly came to my mind that weren't necessarily answered in the book.
So I forgot what requirements we put on the distortion function.
Well, the distortion function is something that is guaranteed to be non-negative, number one, and it's bounded. It means that for all values x, we can't get a x hat that makes it infinite.
But it's not a proper distance metric.
We're not saying anything about that.
So then it could be something weird, and then you can have no distortion.
Well, it's possible. I mean, it is possible to have it be such that there's never an instance where the distortion is zero. Okay. So that let's rule that out. Like by saying that at d is equal to 0, we're saying, okay, it is possible for the distortion to be equal to 0.
It can also be right that there's the distortion 0, but there are errors in the...
That's right. So the first question, that is exactly right. But the first question I'm asking is it ever possible for the entropy to be bigger? At distortion 0, is it possible for the rate to be bigger than the entropy? Which is related, but not exactly correspondent to that question that you just said.
I want to say no.
Yeah, no, because if the distortion is 0, then presumably the error is going to be 0, and if the error is 0, we can compress down the entropy. But on the other hand, which is now the thing that you mentioned, is it possible for the rate to be less than the entropy when the distortion is 0? In general?
Yes.
Yes.
If the distortion function allows error at d equals 0.
That's right, exactly. Expected value, that's right. So, in general, this is the pattern we're going to see. So if distortion is equal to 0, does not require that the probability of error is equal to 0, which is quite possible. Because remember, we said you might quantize a region. Let's say here's our x region, okay? And let's say I quantize it now into, say, 3 regions, okay? And if it's the case that the difference between this value and this value here are not measured by the distortion, we're not going to see distortion, even though they're not equal to each other, and so it's not a zero error case. But the distortion might say, oh, that doesn't matter. I'm perfectly happy with either of those two values. And so what the rate distortion function might look like is the following. That the entropy is here, but the rate at distortion 0 is here. And that's quite likely. That's quite common. But in the case that we just saw, in the Bernoulli case, the one that we're studying, these guys corresponded to each other. Those two red points corresponded. So here we've got, let me just make this clear. So the first point is the entropy point. The second point is the rate at 0. That's this guy. And this guy is the entropy. Okay. So, but what we said is that we can't have the curve be something like, I mean, no reasonable distortion would ever say that this is the entropy. Sorry. That, I guess it would be that the entropy would be below the rate. This would be rate of 0, and this would be the entropy. That wouldn't be reasonable. Unless it's a really, maybe that it's a really bizarre distortion thing. But distortion being 0, the expected value of distortion being 0, it's a positive distribution. It says that for all things that have 0 support, the distortion is equal to 0. So can there be a situation ever where that happens and the probability of error is what? Non-zero? Maybe weird, funky distortion functions, but we're not really going to worry about that. But the point is that this situation is really quite possible. Okay. So then the question is, why is the rate at 0 equal to the HOP in the Bernoulli case? And that's essentially it's a function of the distortion function, because in that case, when the distortion is 0, the probability of error is really going to be 0. So these are identical events in this case, in this current Bernoulli case. Okay. So the key point then, and I hope we've not spent enough time on this, is that the distortion is not necessarily equal to the error. Now the other thing that should be intuitive, we mentioned this last time, is that the achievable rate distortion region is upright closed. Why is that? I said it last time, but let you think about it for a minute again.
What you said was you can always add extra noise bits, and that'll move you up, right?
That's right. And you can always add extra random noise. You can always add extra bits. They're not necessarily noise bits, they're just extra spurious, unnecessary, redundant bits that aren't necessary, that you just strip them off. I could always like add an extra bit at the end of every character. I mean, without, then when you're done with it, so you increase the rate, you're transmitting more, so you can always do that. And similarly, if you achieve a given distortion, you can always get a worse distortion by just adding a little bit of Gaussian noise, adding a little bit of noise. Right? So it's always upright closed. So once you've achieved a point, you can always go up, and you can always go right, and you can always go diagonally up in any direction. Does this mean it's convex? Necessarily? Does upright closed guarantee convexity of the achievable region? Quasi-convex? Well, we're talking about, first of all, a set. Right? A set. What is a quasi-convex set?
It's close enough for me.
It's not convex. So, I mean, like, here's an upright closed region. There's my axes, and what if I do something like this? It's upright closed. Staircase. So is it convex? No. No, anywhere close to convex. It's not even. If you were to define a quasi-convex set, then that wouldn't be even quasi-convex close. So a staircase down to the right would be one example, or anything where you have, it doesn't have to be a staircase. It could look like this, I guess that's kind of a staircase too. But all right, so let's prove this is the rate distortion function. So we're going to assume that x is Bernoulli with probability p, and assume that distortion is less than p for now. And also, without loss of generality, that p is less than or equal to 1/2, and so therefore we can strip out of the min. Just say min of p, 1 minus p is equal to p. So p is the minimum value, and if it's not, then just flip it, so it becomes it. Okay. And so let's define the XOR operator. So x XOR x hat. There's a lot of x's in that sentence. So x XOR x hat is equal to 1 if and only if x is not equal to x hat. Okay, it's this guy. It's the XOR function. And so what we're going to do before, and in fact what we've done is this kind of proof technique. In some sense, the same mathematical technique has been used over and over and over again. So we're going to essentially, in this case, we want to lower, in past when we're computing capacities, we upper bound the mutual information, then find achieving p of x. Now what we're going to do is lower bound the mutual information and find an achieving p of x hat given x. Wow, is it really that late? Okay. So let's do this. So there's the mutual information, and it's represented as the difference of entropies. And the entropy of x XOR x hat is given x hat is the same as entropy of x because XORing it doesn't add or remove any information. Right? But then when we remove the conditioning, that basically increases the entropy and it creates a lower value. And then the entropy of x is equal to p. That's the other thing I want to say. So this is just equals right there. And then the lower bound is this guy. It comes from here. And then the entropy of x XOR x hat is just the entropy of the probability of inequality. So that's an equal sign here, going from here to here. Everything's equal. And lastly, d is greater than the probability of x not equal, the probability of x not equal to x hat. That's the distortion. And if you're wondering why that last inequality is true, I've got a little bit on the next slide that explains it. So basically, the last step follows for the following 3 reasons, essentially, which is that, number one, first of all, we're assuming that P is less than equal to 1/2, right? And then, secondly, we're assuming that D is less than or equal to P, right? So D is therefore less than or equal to 1/2, okay? And secondly, H of D is a non-negative monotone non-decreasing function of D in this range. So remember what the entropy function looks like. It looks like this, right? Where it achieves its maximum at 1/2. So in this region, H of D is going to be sort of this monotone non-decreasing function. It's actually an increasing function. Okay, so H of D is this monotone, and it's only in this region that we care about, because we're never going to, D is not going to be ever greater than 1/2. And then thirdly, we have this constraint, which is the constraint which is true in these cases, because we're minimizing subject to this constraint that the expected distortion is less than or equal to D. So we have the expected distortion, which is here, which happens to be in this particular case that the probability of inequality. That's the expected distortion, so that has to be less than or equal to D. So you combine all those 3 things together, and therefore you get that the H of this probability is less than or equal to H of D, which gives us that last inequality that I put a little green mark on in the previous slide. Okay. So now we need to give a distribution that then achieves this lower bound, because we find the lower bound, and then we need to give a joint distribution that achieves the lower bound and that meets the distortion constraint. And it's actually going to be tight at the distortion constraint. So when D is equal to 0, first of all, having distance requires that the probability of error is equal to 0. So the rate of 0 is going to be equal to H of P. So that we know. But in the case when D is between 0 and P, let's fix this distribution, right? So we fix probability of x is equal to P, because it's a Bernoulli random variable. And so H of x is equal to H of P. And then we're going to choose a distribution, this joint distribution here, that achieves this lower bound, meaning it equals it. Okay, so how are we going to do that? Well, let's do this trick. So what this is going to be, we're going to do like a binary symmetric channel, but from x hat to x. So it's a little bit weird, but I mean, it doesn't matter. Basically, x hat and x, and it's a 0, 1 value with crossover probability of D. Okay. And, we're not actually communicating from x hat to x, and I think one of the reasons, and this is actually something that the book does, that they explain it like a BSC is because maybe they assume that people are more familiar with BSCs than they are with conditional distributions. So what we're really doing is just computing this conditional probability distribution that's symmetric in this sense, that the probability of swapping a bit, remember, if this is 0 and this is 1 and this is 0 and this is 1, probability of swapping a bit is the same, and that's equal to the value D. So we're choosing that conditional distribution, and we're going from x hat to x, right, which is, at first maybe seemingly confusing, but it's really nothing magical. We're not saying that we're communicating in some reverse direction or anything. We're just saying we're choosing this conditional distribution because it mathematically allows us to construct the distribution that we need, which is the joint distribution, which has those properties, namely the distortion property and achieving the lower bound property. Okay, one property we have is the distortion property, and in fact, when we choose this conditional distribution in this opposite direction, then no matter what P of x hat is, we have that the expected value is equal to D. The expected value of the distortion is equal to D. And the reason is, you just sort of put that into place, because the expected value of the distortion is, remember, the sum over x and x hat of probability of x given x hat times the probability of x hat. But then we strip out the outer sum over x hat, and we've got D. D is the resulting distortion, and so we have P of x hat times D plus 1 minus P of x hat times D, which basically sums up to D. Okay. So, and that's irrespective, that's irregardless. That's regardless of P of x hat. So we can then we just got that right away. And then secondly, now what we're going to do is say, okay, well, if we're constrained by essentially the probability of x being P, what does that give us for the probability of x hat? What is that distribution? So we solve for it. We say, okay, well, probability of x being 1 is equal to p. We unmarginalize out x hat. So we're just sort of summing over. This is just the joint distribution expanded using conditional probability and Bayes' rule, which hopefully everybody's familiar with at this point. We have a constraint on this and this, so we can write it one minus the other. We know that that this guy here is just the switching probability. This is the same as this, and they're both equal to d, right? Why? Because we're assuming this. Right? Conditional probability, they're the same. It's symmetric. Sorry, let me take that back. That's a bug in that's a iPad O. This is 1 minus d. Is that better? That's better, I think. Yeah, there you go. So then we get this. Here's the d before, and here's a 1 minus d there, and then we have everything in terms of the probability of x is equal to 1. These two things there. And so then we relate this p to this expression, we can solve for p of x hat is equal to 1, and we get this expression here, just algebraically. So that gives us an expression. Now, one of the things we note is that this is going to be less than or equal to p whenever d and p satisfy this constraint. So d again is no greater than 1/2. So, because p is no greater than 1/2 and d is less than p. Okay. And if you're not comfortable with this inequality, this is the same thing we did last time. So this inequality we want to show now, why that's true, under this condition. So why is this green inequality true under the yellow condition? Well, let's just again set up the problem. We just say, okay, here's the condition and here's the expression. Then p is going to be greater than that expression. And it's just by algebraic. You just sort of show p minus d over 1 to d minus p is equal to this thing. And since p in particular is less than or equal to 1/2, 2p at most is equal to 1. And if anything is going to be less than 1, and we subtract off 1 from it here, we're going to get negative. The denominator is always going to be non-negative, because d is strictly less than 1/2. And so this thing's never going to be negative or 0. The numerator is going to be negative. So therefore the whole thing's negative, and so p is therefore greater than that expression. Okay, so we have the right distortion, and we have an expression for probability of p hat. We just need to show that the mutual information under these distributions is equal to this lower bound. And then starting with the lower bound, we just say, okay, here's the actual lower bound, and this is less than the mutual information, which is equal to h of x minus h of x given x hat. But h of x is equal to p, but h of x given x hat, thanks to that distribution we have, is just equal to the entropy of d. And why is that again? I mean, we just plug in that conditional distribution. P of x given x hat is log of p of x given x hat. That's just going to be equal to d. It's just equal to the entropy of d. And then we sum up overall p of x, but it's symmetric, and so therefore that part cancels out. And so therefore we've achieved the lower bound. So we're not done yet with this theorem, because we said, okay, what happens, first of all, when d is equal to 0, one thing we need to check, when d is equal to 0, that this expression down here at the bottom has to approach the h of p point, right, which is the entropy of the source. And when d is equal to 0, the distortion is equal to 0, h of d is also equal to 0. So we're covered there, right? So we get h of p, which is what we should get, right? But what happens when d is greater than 0? Or sorry, what happens when d is greater than h of p? The rate I mean, this expression becomes invalid because it becomes negative, right? But what we wanted to do is prove this inequality is that when the distortion gets bigger than the probability of P, we don't have to do anything to achieve that distortion. We don't have to compress at all. We can just have a zero rate code. And so how do we do this? We need to show that we can achieve a distortion of D whenever it's greater than or equal to P with a rate of zero code. And so what do? If you say, okay, well, I want to have a distortion of P or greater. And I say, okay, I'm not going to store anything. I'm just going to store a bunch of zeros. I'm just going to hard code x hat is equal to 0. So I'm just going to store 0. I mean, I'm not communicating at any rate. In fact, I could just count how many zeros. I don't even need to do anything. The decompressor just says, give you zeros. Lossy decompression. I mean, that's not a very good code. If someone came out with a camera and did J compression down to 0 rate, and then every picture was just a blank, that would be a lot of distortion, but it would be bounded distortion. And you could say, hey, my JPEG image is compressed really, really well, right? But you wouldn't be very happy with it. But that's essentially what we're doing here. A rate of 0. So why is there a rate of 0? Well, okay. The probability of error, when we do this, needs to be so bounded. So what we end up getting is that the expected distortion. So let me just make sure this is clear. Is it clear that we're getting a rate of 0 by doing this? Okay. So by doing this, we get a rate of 0. We need to make sure that by doing this, our distortion is equal to P. Okay. And so the distortion is the expected distortion here, which is really just the probability of the error. And the probability of error is this. It's the probability of x is equal to 0 times P of x is equal to 1, given x is equal to 0, plus this. But this whole bit here is just going to cancel out, because x is never 1. And so we just get that the probability of x is equal to 1, which is equal to P. So our probability of error is P. We've achieved that rate of distortion with the 0 rate code. We've achieved that level of distortion with the 0 rate code. And again, once we've achieved a point, once we've got this point here, we can always move to the right. That's easy. So all we needed to do is achieve that point, and we got this whole bit covered. Okay, so this is a key theorem, and given the rate that we're going, so this is a good example of showing a class. Like, teaching is a rate distortion function. I could go at a faster rate at the expense of more distortion, or I could go at a slower rate at the expense of less distortion. So at our current rate at distortion level, I'm not sure we'll finish the proof of this theorem, but what we want to do is understand this theorem. And that's basically saying, as you might not be surprised to find out, saying that the left rate distortion function, which again is the infimum of achievable rates at a given distortion, the left rate distortion function, which is the infimum of the achievable rates at a given distortion, is equal to the right rate distortion function, which is the result of the optimization problem. Okay, again, exactly analogous to the channel capacity. So there's two things to prove. One is that if a given pair, RD, is achievable, then it has to be the case that R has to be greater than the rate distortion function. And again, and then the converse says that if rate is greater than the information rate distortion function, then there exists a sequence of code such that as the block length gets long enough, the distortion eventually it gets to that, arbitrarily close to that distortion. And also very, very similar to what happened in the channel capacity case, what happens at exactly this point? Like, when is it equal? It depends on the case. In some cases, we can set up an artificial example where it's exactly equal. But in general, the theorem just says you know, this is sort of the limits of achievability. It's the infimum. Okay. Infimum of achievability. And so if it's like an open set at the bottom, then infimum just gets to that boundary, closes it. So the plan is the following. It's like what we're going to do is spend, before proving this theorem, which we might assume, but we want to, of course, prove it. But I wanted to do a couple of instances of Gaussian, because the Gaussian, there's two instances of Gaussian channels. One is just a regular Gaussian channel, and the other is when you have multiple Gaussian channels with different noise, different power values, and there's a joint distortion constraint on all the channels. And so those are represented in these, this stuff up here and this stuff up here. But maybe this is a good time to take a break. Are there any questions before the break? No? Okay, so let's pause. And after the break, let's pause just for a short time. Okay, so let's move forward now. So here's the rate distortion function, the information rate distortion function for Gaussian sources. So what does this mean? So it means that x, what is x? X is no longer discrete. X is Gaussian, scalar, with mean 0. Its means don't matter. And variance sigma squared. Okay. And we're using a squared error distortion, which is the one we saw before. It's just basically x, it's the square of x minus x hat. And then we have a rate distortion function that looks like this. So here's this. So basically it's that form for the distortion between sigma squared and it's 0 otherwise. And so it has the same form, the same profile that we saw before, namely that if we were to plot the axes and then we were to plot the distortion itself, it would go down like this. And in this particular case, this point would be at sigma squared. The axis is a function of distortion. So one thing to note, which is a little bit different, and maybe if I were to draw this a little bit more carefully, see that the rate goes up like this, right? So why does that make sense? So when d gets very close to 0, I mean, you can see either from the log form or from this beautiful plot that I just created that the rate gets very, very large and goes to infinity. Why?
So we said that for a Gaussian channel, if you have no power constraint,
yeah, very good. That's right. So because it's exactly analogous to essentially, transmitting or essentially compressing, or essentially the information that can actually be represented in a Gaussian without a power constraint. Right. So we may need to, for example, store an infinite precision integer because we're saying, okay, there's no distortion. Okay. So, right, so at 0 distortion, we're needing to code an infinite resolution Gaussian, which would require an infinite rate. It's exactly analogous. It's almost as if you saw this slide. Maybe you did. Maybe you wrote this slide. No. Do you have the slides? Because you actually have all these answers. I mean, if those of you who are looking at the slides, and when I ask these questions, these aren't meant rhetorically, these are meant thoughtfully. And so hopefully one isn't sort of looking ahead at the slides. Actually, since nobody's answering the questions when I ask them, I don't think anyone is doing that anyway, so I think we're fine. But in any event, let's derive this function. So here's the derivation. The equations are not appearing one after the other on this slide, but that's okay. I will highlight them in yellow as we talk about them. So what we're going to do is we're going to lower bound the mutual information subject to this distortion constraint, which we're making, which we're assuming along the way. So here's the actual form of the thing we're trying to compute. So this is the optimization problem that we're trying to find a solution for. So we start off by saying, okay, the mutual information can be represented as the difference in entropies, standard. X is Gaussian, and so it has an entropy that looks like this, right? And the entropy, the residual uncertainty in X given X hat is the same as the residual uncertainty of X minus X hat given X hat. So therefore, this thing and this thing are the same. Okay. Next, we have that conditioning basically reduces uncertainty. So when we don't condition, we increase the entropy, or can only increase the entropy, so we get a lower bound. Okay. Fine with that. Next, we have that a Gaussian is the distribution with a max entropy for a given variance, and the variance of a source of x minus x hat is going to be the expected value of x minus x hat, because they're both zero mean. But then we said, oh, we're assuming the distortion constraint. This distortion constraint is assumed to hold true. And so therefore, this one. And so therefore, that's a further upper bound, and we get the distortion here, which gives us a lower bound. And then we just combine the logs, and we get -1. We get 1/2 log of sigma squared over d. Okay, so now we've got this lower bound. So what we have is that this quantity, the mutual information, is an upper bound of this quantity here. And now we have to do the same trick before, where we find an achieving distribution. And to do so, what we do is, similar to before, we construct a channel in some sense the reverse direction by giving a conditional distribution of f of x given x hat. So we're giving this quantity here. It's exactly analogous to what we did in the discrete case. So here's our inverted channel. So let's just zoom in on this a little bit so we can all see it. So the input is x hat, and it's a Gaussian with variance sigma squared minus d. The output is going to be x, which is a Gaussian also with variance sigma squared, and the noise is going to be z, which is a Gaussian with distortion d. And so when you add z and x together in this fashion, what we're going to get is an x with a noise sigma squared. Okay. So again, z and x hat are independent. The other thing to note, again, is that the expected value of the difference, which is equal to the expected value of z squared, is going to be less than or equal to d. So we are actually at the distortion. We are satisfying. We're feasible with respect to the distortion constraint. Okay, so that's good. Now you might think, where did these come from? These came from using the same trick, and then just setting the variances just so that these things work out, as you'll see. So the mutual information then, at the bottom, is the difference of entropies. X is again Gaussian, and the entropy of x given x hat. So given this guy, given x hat, the entropy of x is entirely determined by the entropy of z, right? And so that's therefore equal to the entropy of z. And so we now have thus achieved the mutual information is equal to the quantity that we want. Okay. Everybody happy? Now, very similar to what we did last time, we have to, so when the distortion goes above sigma squared, when d is greater than sigma squared, it's the log of a value that's less than 1, and so this rate again becomes negative, which again doesn't make sense for a rate. But, what do? I mean, essentially we fix that. We say, okay, well, wait a second. Once the distortion reaches sigma squared, again, I can achieve a zero-rate code. I can just send north or do something arbitrary. So how do we do this in the Gaussian case? We're just going to send or store or decode zeros again with probability 1. And that, when we look at the expected distortion, thanks again to the variance of x, of the input source symbols, that's going to be a distortion that's going to have exactly equal to sigma squared. We've now achieved that distortion by this method without actually having to do any coding at all. So therefore, we get the final resulting rate distortion function of this form. So just as a reminder, I mean, this rate is always achieved by longer block lengths. So so to get this rate, and again, also this doesn't tell you how to do it necessarily. It just says that there exists. We might need to use a long block length. These are the limits of achievability. These aren't the actual. This doesn't say that you can go out to the corner store and buy a compression algorithm that achieves this rate and distortion. You might have to work for it. You might need to use long block lengths. You might need to be clever. And I think this last sentence I've said now a couple of times, but keep this in mind. Okay, any questions about this? Everybody at least get the idea. Anybody have any questions on the derivation? And the derivation it's mostly algebra. A couple of tricks here and there. Information theoretic. We're very comfortable now with information theoretic quantities. So we're using them fairly blithely, in some sense.
So everything that I compress in my day-to-day life is like bits and not Gaussian, right? When do I compress
It's like bits?
Like if I zip a file on my computer or I'm doing discrete compression.
Well, I mean, when the information really is, I mean, again, in the context of a Gaussian channel, we're measuring it in units, information units, but what we're sending out are continuous signals, and so we want to understand, like in the Gaussian channel case, what's the capacity, what's the representational capacity of a Gaussian channel that's power limited in this way when subjected by a channel which has got this particular noise profile, right? Because that's a context. There are contexts where you're sending real values, like when you're sending an analog voltage value or you're transmitting a radio transmitting an analog voltage value wirelessly. Those are not bits. I mean, the world is an analog world, and the computer offers this paradigm that allows one to think in terms of bits. But in fact, once you actually get to what's actually stored on a disk drive or on a SSD, it's not actually a bit. It's some, not necessarily quantized, value. And people are working on, single electron-based storage, so that maybe there is some underlying physical quantization going on. But for the most part, I mean, when you think about voltage values or signals, it's a continuous world. We haven't yet gotten down to that. And that gets into sort of a realm that's beyond this class, really. What's the structure of nature? Is there a fundamental quantization of nature somewhere down at the lowest level? But in this particular context, in the Gaussian channel, we're saying that how much, in some sense, information is there in a Gaussian source if we're willing to admit some degree of distortion. So we have a capacity, right, of a channel. And let's say that the capacity of a channel that is subject to some noise puts some bottleneck, it puts some limit on how much information you can send through it. And let's say I've got some Gaussian source which has got more information than is needed. And this says, okay, well, I can first compress the Gaussian source that by adding some distortion, in some sense, at a loss of some information, but at a gain of some distortion, right? And maybe that's enough to sort of squeeze it through the bottleneck. So I can get perfect information sent of my compressed, losslessly compressed Gaussian source. And so that's what this is really talking about. So what I mean, it's in some sense, dual to the channel capacity theorem, because when I decompress, what it's going to be like is basically my original Gaussian source that's been subject to some noise. But the bit distortion is going to be bounded. And if you've done that process, then you're saying that if that distortion is acceptable. But, I mean, this is one model. I mean, so the whole idea is that, again, these are models of the real world. And information theory is basically coming up with essentially a set of tools that allows us to analyze a particular model as to its qualities. And network information theory, which we're going to be studying at the end of this course, is essentially coming up with richer and richer models of the kinds of scenarios, communication scenarios that we have in real problems. And so is this model a particularly good one? No. This is one that we can study analytically because it gives us, we can actually compute the exact rate distortion function. Analytically, there's one case statement, right? But other than that, it's a nice log function. In real instances, one can never really do that. And instead, what one has to do is computationally compute the rate distortion function. And that's one of the reasons why people are interested in computing the rate distortion function for a given, maybe we only have measurements or some aspect of some model, we don't know what it looks like, but that's what the Blehard-Aramoto algorithm does. It allows us to plot the rate distortion function, even though we don't have an analytic expression for it. You can run it in MATLAB even. But what we're doing here is we're doing these sort of, in some sense, relatively simple models. So the next step, and in fact this is sort of going into the next step, what we're going to do is we're going to enrich our model slightly. And as you can see, even if we do a little bit of enrichment, the analytical difficulty increases quite a bit. Now we did that in the case of the Gaussian channel. Remember we said, okay, we first start off with a bunch of independent Gaussian channels, then we said, okay, we've got now a joint power constraint, that the sums of the inputs have to sort of together sum over each, even though they're independent Gaussian channels and the noises are independent. Now we're putting a joint power constraint, which suddenly meant that we had to do optimization. So this is similar to what we're doing here. It's a similar analogous step, because what we're going to do is say we've got multiple Gaussian channels. It's not a joint power constraint, but it's a joint distortion constraint. So each Gaussian channel has it corresponds to a source with a different variance. I mean, it's really Gaussian source symbol. So we've got m of them. Each one has its own variance or its own power, sigma I squared, and they're not required to be equal. And we have a distortion, a joint form of the distortion. So it's the squared error distortion, but it's the distortion over m symbols. And we have an expected distortion. So expected distortion is over this joint distribution. Right? Now the joint distribution, let's going in here, zooming in a little bit, is basically, it's not what I want to do, it's this, right? We're taking the expected value over this joint distribution. So we're not saying, I mean, we know that the x's are independent, but once we represent everything in a joint distribution, it doesn't necessarily mean that everything is independent. Okay? And we're saying that that has to be less than or equal to d. Okay? Is everybody with me on that? So like I said, it's analogous to what we did in the Gaussian channel case. And so we have a rate distortion function form that is the following. So it's basically, again, it's a minimization over the mutual information. There's the same quantity, but we have this constraint. We're minimizing over these conditional distributions. Because remember, the only thing that we can control that we're optimizing over is this conditional distribution. We don't get to control the source distributions. That's fixed. And we know they're Gaussian, we know their variances, we know they're independent, but other than that, we know everything about them up to at least their distribution, but we can't control them. What we can do is control the distribution, the conditional distribution, jointly, such that we need to satisfy this constraint. Okay, is everybody comfortable with the objective? So this is hopefully something we'll finish today. So this is in some sense like we need to know how many bits to allocate each source symbol, and or whether to allocate any bits at all. So remember, the number of bits each source symbol gets is a rate, and each source symbol then gets to communicate at a particular rate. And it might be the case that we want to sort of compress it down as much as possible, subject to these distortion constraints. And if the distortion gets too big, maybe some of these guys will get turned off. Maybe some of them, but they will get turned off at different points. So what we're going to see, and this is sort of getting to this famous inverse water filling description, as opposed to the water filling description, we're going to see is that as the distortion gets bigger and bigger, it's not going to be the case that we keep allocating fewer and fewer bits to everybody. At some point or another, what's going to happen is some of these sources are going to get turned off, meaning that we can effectively, even with this joint distortion constraint, what's going to happen is that some of the sources are eventually going to be allocated at zero rate, meaning that we can achieve the overall minimum is achieved at a point where some of the sources are completely off, and we've got the overall distortion by essentially turning them into just random nodes, or not communicating them at all. And we allocate our efforts in such case to the sort of higher, and you can imagine that the ones that are going to get turned off sooner are probably the ones with what? The lower variance, right? And that's at least what makes sense. That makes intuitive sense. Okay, so let's find this lower bound. That's what the any guesses was meant to sort of convey. So I gave you some guesses. What's happening here? Did we lose our screen? Okay, 1 second. Okay, we're back. So what we're going to do is expand the mutual information in order to achieve a lower bound. So we do this by this step first, which is just the definition of mutual information as the difference between two entropies. The first step here we get because the x's, the m source symbols are independent. So that's not a bound at all. That's just an equality. And then the second one is just obtained from the chain rule of probability. So we're just conditioning on everything in turn. Okay. The second one here, this guy's inequality that doesn't change. But now what we're doing here is we're saying conditioning reduces entropy. And so we're not conditioning, thereby making the conditional entropy bigger, or we're doing less conditioning, and since it's a minus, we're making the whole thing smaller. But now we have it in a form where we can combine the two things together, the corresponding terms of the two sums together into the sums of mutual informations. And once we have it in this mutual information, we can reuse the work that we've done before by saying, okay, well, this is lower bounded by this rate distortion function, but in this particular case, we've got a distortion associated with the ith source symbol d sub I, which we said has this form. Right? This is the form. And again, the distortion is, in this particular case, equal to the expected value of the difference squared. So that's pretty easy. To achieve equality, so we've got the lower bound, now we want to achieve equality. To achieve equality, what we do, we can actually get that by, first of all, using this conditional distribution where there isn't any interaction amongst the set of source symbols. So that's actually, it turns out, not going to be necessary. So it's a much simpler conditional distribution than what we had originally perhaps assumed by using this more general form in the optimization expression. Namely, it's possible to achieve equality by essentially making this as a product of conditionals associated with each of the scalar pairs of x and x hat for each I. And similarly to what we did in the individual Gaussian channel case, we're going to make x hat equal to a Gaussian with sigma I minus di, except in this particular case it's associated, it's an individual d and an individual sigma squared for source symbol I, as opposed to a generic one. And that is what we're going to call sigma hat squared. If anyone can see that, notice that there is a hat here, but there's no hat there. So, did anyone not see that? My eyes are really bad. I can't, in fact, right now you all are a big blur to me. I can't even count how many people there are in this room on one limb.
There's 45 of them.
45 of you? Okay, that's good. I thought it was more. I thought it was like more like 60 or 70. Okay, so the problem becomes the following. So we're going to, it's an optimization problem. We're going to minimize over the set of distortion values, because remember, that's in some sense what we want to do. We want to minimize over the set of distortion values such that summing them up is equal to d of this max, of this sum of maxes. Now this looks a little bit tricky, but it turns out that maxes are easy to express in an optimization problem with auxiliary variables. And this is an optimization trick. And then I'm sure that in the convex optimization class, one of the things that one does is go through lots and lots of problems and you say, oh, look, I can express this with a bunch of additional auxiliary variables and constraints. And so I'm taking the maxes, and each one of these maxes I'm going to say, okay, it's a rate. So I want to minimize over the sum of rates where we have two constraints. So we can represent a max as two constraints because we're minimizing the max over this, so we're minimizing over R, where R has to be greater than each one of the things that lie within the argument of the max. Right? And of course, if we minimize that, we're minimizing exactly the max. But now we've got some additional variables. So that's really easy to do. And we still have this constraint here, of course, as well. So now we're minimizing over auxiliary variables R and D. But it turns out now that we've introduced these auxiliary variables, we're going to be able to get rid of them. This might seem circular or circuitous, I should say, but it's actually not. It's not circuitous from a perspective of gaining an intuition as how one actually solves it. Because if it's the case that if we say that the distortion I for source symbol I is less than the sigma I, then each one of these rates are going to be greater than 0 strictly, right? Because whenever looking at this inequality, this guy here, let's zoom in on it a little bit. So whenever, so what's going to make the rates strictly greater than 0? Well, when sigma squared is greater than distortion I, right? That's going to make it greater than 0, and so in some sense, that guy becomes irrelevant. And whenever that's not true, the rate just turns off. It's going to reach 0. So this is where sort of we're getting intuition as to what's going to happen with things like the KKT conditions. Because whenever the distortion is strictly less than the variance, we can essentially avoid all of the constraints R. Or all of the variables R. All of the constraints on R. And so this gives us the following Lagrangian. Again, in this case. So now we have one Lagrange multiplier on the sum of di is equal to d constraint, which is expressed here. By the way, I forgot to mention that this is, everything is a convex optimization problem. It's a convex minimization problem. We've got strong duality and the KKT necessary conditions for optimality. So we've got all of those tools to help us yield the solution, so we can construct the Lagrange multiplier take the derivative, set it equal to 0, and so what we end up getting is that d is equal to 1 over 2 lambda, but more importantly, it's really d of I is equal to lambda prime for some constant. It's basically all of the d's are the same. Whenever we have this being true for all I, all of the d's take the same value. So this says that it's we can use the same distortion amount for all source symbols, which is feasible. So we just solve for lambda prime, and then that becomes our solution. So, like for example, whenever it's the case that lambda prime is, say, d over m, it's like divide d into m equal pieces, and if that's less than the smallest sigma, sigma squared min, then everybody gets to transmit. Okay? Everybody does transmit. On the other hand, when we start increasing the distortion, what's going to happen is eventually this lambda value is going to hit this lambda value is going to hit that minimum guy, or maybe there's going to be not a unique minimum, maybe there's going to be multiple guys, but the lambda is going to hit that value, at which point we can't say that d is because remember lambda prime, this lambda prime is equal to the di for all I, but as we increase the overall distortion, d over m, which is equal to lambda prime, which is equal to di, is eventually going to hit some sigma. And this condition here is no longer going to be true, at which point the rate has to turn off. So as the distortion gets higher, the lambda gets higher, and the rates turn off. So whenever this lambda value is bigger than any of the, is equal to or bigger than any of the sigma squares, there's no rate, meaning we're not transmitting. So in other words, as the overall distortion increases, the corresponding lambda, this should be lambda prime here, this lambda prime will also increase, eventually hitting one or more of the sigma squared values. And this is still lambda prime here. And it shuts off some of the distortions. It shuts off some of the sources, meaning they communicate at a rate of 0. So, I mean, this is essentially the KKT conditions again that we use. And so what we end up getting is this solution. We get that the rate distortion function under the squared loss joint distortion has the following form. It's this, where d of I is equal to lambda whenever lambda is less than the ith variance, and it's equal to sigma squared when lambda is greater than or equal to the ith one. And when d of I is equal to lambda, that's going to be log of this part here. Log is going to be 1. It's going to be log of sigma squared I over sigma squared I. That's just going to be 1. It's going to turn off that rate. That rate's going to be 0. So that the ith source in such case is not going to communicate. And where otherwise we just communicate, we just sort of choose the lambda such that the resulting distortions we just sum the ones that are set to these values, sum up to d. So this might seem a little bit confusing, but this is the inverse water filling argument. So if sigma is too small, we allocate no bits. And I think the best thing is to look at a picture. When sigma is large, we do allocate bits. We do communicate. And here's the actual picture. So what's actually happening? Let's just zoom in on this picture a little bit. This is one of these beautifully hand-drawn pictures. So the current value is lambda. So remember, the things that we're summing up, so all of this stuff that I'm going to highlight in green is the sum of the distortions. And all of these distortions have to sum up to D, which is our overall distortion constraint. Here's the value of lambda here. This is lambda. And so the only one, so this rate, so R2 is going to be is equal to 0. R3 is equal to 0. But R1 is greater than 0. R4 is greater than 0. And R5 is greater than 0. Okay. And the rates are given by 1/2 log of sigma squared I over D, right, where the D's are set to all equal to lambda. And I guess this is lambda prime here, okay, using what we were saying before. So you can think of this like inverse water filling. Why? Because think of it as like you've got these bins sort of hanging upside down with gravity pointing in the up direction, and it's raining up. And this lambda line sort of gives a new bottom of the bin. So either the bottom of the bin is here, it's like this point here, or the bottom of the bin is here whenever it's less than the sigma squared. And so the rain basically fills up all of these bins, but it never goes below. In this case, really, it's above because we're sort of thinking of inverse water filling. We never go above lambda, and so all of the green stuff is filled with rain in this inverse water filling kind of way, where it's raining up. And we do that until we fill it all up with water. We fill it up to 0, and we do that so that all of the D's sum up to DI sum up to the D, the distortion constraint. And I don't think this is this isn't as beautiful and as natural as the original water filling argument for Gaussian channel, but I think it's maybe it's one way of thinking about it. Okay, any questions?
So basically, we try not to transmit those sources that are like deterministic, right?
Yeah, I mean,
allocate this to those that we have to answer.
I'm not sure I'd call it deterministic, but I mean, in some sense, they have rates of 0. Like these guys here, these ones, these two, have a rate of 0, so they're turned off. They're not transmitted at all. It's only the ones that have greater signal power that get transmitted. But like I said before, what happens is it's not that the rate slowly goes to 0 but never gets there. It's like the rates go down and they get shut off. Sorry, the distortion is big enough to allow me to just completely turn off those guys. I don't even need to allocate any bits, and I can still achieve the best solutions. I can still achieve the overall distortion constraint by only allocating bits to these other guys. Obviously, if the distortion is very small, I have to transmit. Everybody gets a rate. But at some point, when eventually this sort of joint distortion hits one of the variances, then that guy gets turned off. Right? So if as soon as lambda prime hits sigma I squared, then channel I gets turned off, meaning it has this rate of 0. And then to recover it, I can do my x hat I is equal to 0 with probability 1 type recovery, and I still achieve my overall distortion constraint. So it's kind of intuitive. I mean, we didn't go through all the actual KKT conditions in this case, but this is essentially a consequence of that, which you can go through. And we've got a lot of notes on the KKT conditions a couple of lectures ago. Okay, I think we need to go because we're going to get kicked out. So I will see you guys on Monday. Have a good weekend. So this week there's only one lecture.